Okay, so the first thing we know is that yesterday we talked about how e to the x and a to the x are both very smooth, right? So we believe they have derivatives. And we went through this long rigmarole and showed that e to the x is its own derivative. So we did that. And then we also know that e to the x and a to the x are differentiable for all x. They have no horizontal tangents anywhere. So remember from the 3.7 day 1 lesson, that means that they each have an inverse that is differentiable. For all numbers in their domain. Okay? So, it turns out that we know e to the x is a positive function. That just means it never gives you a negative number, right? If you give me a number, let's say 100, and I plug it into e to the x, I'm going to give you a positive answer. If you give me x equals negative 400, it's still e to the minus 400, which is a small positive number. So exponentials have a positive range, and that means their inverses will have a positive domain. The domain of any logarithm is x is greater than 0. If you didn't understand that sentence, here's what I'm saying. We believe that e to the x is very smooth, no corners, no cusps, no vertical tangents, no breaks. Because of that, we believe that its inverse, which is simply a reflection over this line, whose name, by the way, is ln, we believe that that graph will have no vertical tangents, no cusps, no corners. Actually, we believe it has no vertical tangents because e to the x had no horizontal tangents, see? So when we flip it over that line, it should be perfectly differentiable. It does have a domain of positives only. There's no such thing as, ln of -1. That doesn't make sense. Even ln 0 makes no sense. You can only ask questions like, what is ln of, and then state a positive input. But I believe with all my heart that there are tangent lines on here and that they all have a slope. I believe that. Okay, so now I'd like to know the derivative. So what is the derivative of ln x? Well, we can start with the fact that we're trying to find the derivative of ln x and just write it like this. But if it's too threatening, we'll just e both sides. So let's e both sides. This will be e to the y. And this will be e to the ln x, also known as x. And I'm not scared of this at all. I can do the derivative lickety-split. So the derivative of e to the y is what? What's the derivative of e to the y?
E to the y, y prime.
E to the y prime. And the derivative of x is simply class 1. Okay. So I get y prime equals 1 over e to the y. But y is ln x, right? Originally they gave us y is ln x. So let's just change the y to an ln x. So it looks like this. Y prime is 1 over e to the ln x, also known as 1 over x. One over x. So what a simple derivative, like 1 over x. It's that simple, really? The derivative of ln x is 1 over x. How about that? Okay, so I'm just going to show you something graphically real quick. Okay, this is the graph of ln x, and we believe that the derivative is 1 over x. So let's see if that makes sense. So I can click on the derive button. This is a cool button. Watch this. Except it's not working. Why aren't you working? Derive? Are you not comfortable with that function? Okay, I'm sorry. I didn't mean to intimidate you. Are you freezing up because you don't like me? Okay, we'll talk later. I'm not sure why you're so upset. There we go. There we go. Let's try that again. Derive. There we go. Look at that. 1 over x popped up. See it? Here, I'll hide it. There's ln x. Here comes 1 over x. Watch. Bam, 1 over x. Look at that. Pretty nifty, huh? Look familiar, that function? 1 over x? Quick talk, right? Okay. So it's a good thing we know that, because what if I gave you the instructions to take the derivative of a function. I would like you to find the derivative of a function, and it comes out to 1 over x. You might be like, oh, I know. This is x to the minus 1, right? So that means that it's some function that has 1 greater power, right? Because when you take a derivative, you take away a power, right? But that doesn't seem to make any sense. Because wouldn't that mean that f has degree 0? So f is like something to the 0? But that doesn't make sense, because when you bring the 0 down, it would disappear. So this particular function troubled people for a long, long time. What function has the derivative 1 over x? What is it? What is it? What is it? Turns out it's ln x. Ln x. So that's a very interesting phenomenon. Okay, you don't need to know the origins of it all. You need to know this right at the bottom of the page. The derivative of ln x is 1 over x. Okay, that's what you need to know. All right. So that means if you're doing the derivative of ln of something else, let's say happy face, you're going to need to do 1 over happy face times the derivative of happy face, also known as happy face prime over happy face. Okay? So the prime means d dx. So this is derivative of happy face over happy face. I don't think I answered your question. What's your question?
Wouldn't the x in d over dx also be a happy face?
No. If it was d happy face, ln happy face, if it was, excuse me, I said that wrong. I meant to say dd happy face of ln happy face, then I would just do 1 over happy face, and the chain rule wouldn't be necessary. It's when these disagree, right? When this is something different from what you have in your argument, that's when you need the chain rule. So this would be times happy face prime. Okay, so what about log base a of x? So what if it was some other base? You know, logarithm base e, we call it ln, right? But there are other bases, log base 2, etc. So how do you do those? Well, why don't we just run through this here. Why don't we write it as y equals log base a of x. And this is intimidating. I don't know how to do logs yet, right? So I'm going to move this over and call this a to the y equals x. It's the exact same thing, just inverted. Notice there's no logs. So the derivative of both sides, if we do the derivative of the left side, what's that give us? A to the y ln a, right, times y prime equals 1. Okay, so we get y prime equals 1 over a to the y ln a. But y was log base a of x. Remember up above here in blue. So this is going to be 1 over a to the log base a of x times ln a. And then this part just cancels out. And you get 1 over x ln a. So the derivative of a log with a base other than e is almost 1 over x, but there's an ln a on the bottom. I won't write the happy face version. It's too messy. So what we're saying is, it's really very simple. If you take the derivative of ln something, it's just 1 over that thing times the chain rule, you know. But then if you're doing log of something else, you have an ln a that pops up, just like we had with derivatives, only this time it's on the bottom. On last night's homework, it was, up top, right? So let's go on and try some problems now. Okay, so for my first problem, I would like to do find dy dx of y equals ln of 10 over x squared and y equals log base 3 of 10 over x squared. The answers are quite similar. Okay? They're very, very similar. The only difference is the second one has an ln 3 on the bottom. Okay? That the other one doesn't. All right, let's get started. So first, y equals 10 over x squared, ln of 10 over x squared. Okay, so what you're supposed to do is understand that this is first and foremost a logarithm. So you're just going to do 1 over what's inside. And then you're going to do the derivative of what's inside. Well, this means 10x to the minus 2, right? So that's going to give us negative 20x to the minus 3 for a derivative. And if you're careful and you combine this properly, it just comes out to negative 2 over x. As for the other problem, find the derivative of log base 3 of 10 over x squared, I don't need to. It's the same problem. There will just be an ln 3 chilling on the bottom. So let's do y equals log base 3, 10 over x squared. The derivative is going to be same answer with an ln 3 right here. I want to show these two side by side because I want to show you that they're really very, very similar. I don't want you to get lost in the notation. We have one basic idea. If the base is anything other than e, you need an extra little ln on the bottom there. Okay. Let's try another problem. What if it's like a trig mixed in with like e and stuff, That can be kind of intimidating. But they kind of make for fun problems too. So watch this. Let's find y prime if y is equal to e to the, which one did I pick? Oops. Sorry, I got a little mixed up here. I meant to say, find y prime if y equals ln of, and let's do cosine x. Okay? Now we have to be careful. Cosine there cannot be negative. You cannot have negative inside of a log like that. So we're going to go ahead and say for x's between 0 and pi over 2. We just want to make sure we don't have any negative in the inside of our log there. Okay. So first and foremost, it's a logarithm. So you're going to do 1 over whatever's inside. So what's inside is a cosine x. So we have 1 over cosine times the derivative of what's inside, which of course is just negative sine x. So it's kind of a fun problem. This answer turned out to be negative tangent x. Negative tangent x. Not so difficult. So it's 1 over the inside times the derivative of the inside. Let's go to the next one. A line with slope m passes through the origin and is tangent to the curve y equals log base 3 of x. Find m. Whoa. Remember, we always have to talk about tangent lines. If we're going to learn a new derivative, we're going to do a tangent line problem in that lesson. Okay, so I'm trying to understand this. It's saying that we have the graph of log base 3, that, by the way, passes through the point 1, comma 0, like every other log, and it passes through the point 3, comma 1. All logs pass through 1, 0, and all logs pass through base, comma 1. Okay, so in this case, 3, comma 1. All right, so there's your graph. Now I've got a tangent line. Tangent line, like that, passes through the origin, and it hits the curve. I don't know where. Where does that thing hit, you know? It's not a very straight line. Okay, but I'm hoping to find the slope of that line. So this is my best first step. The first thing I can do on this problem is I can at least draw what they're asking for. Right? You should always draw a picture. Sketch to see if you understand what it's asking. I want the slope of that line. Okay, let's do it. Okay, I got a problem though. I don't know where that point is, that one on the right, the second red point. So what I need to do is understand that this line has slope y2 minus y1, right? All over x2 minus x1. Although I don't know what point this is, I can certainly call it, I don't have to put question mark, question mark. I can at least write this, can't I? K, comma, log base 3 of k. I mean, I might not know where that point is, but at least I know it's on the log 3 graph. So whatever the x value is, the y value will just be log base 3 of that. So don't put question mark, put k, comma, log base 3 of k. All right, so what is the slope? Well, it would be y values subtracted for the two red points. Over x values subtracted. So the slope is going to be log base 3 of k over k. Good to know. That's a start anyway. The other thing I know is that that's a tangent line. Right? That thing's a tangent line. So that means that m is also f prime at k, isn't it? It's also the derivative at k. The derivative at k is the slope of the tangent line. So not only is m rise over run, it's also f prime at k. All right. So if f is log base 3 of x, then the derivative is going to be 1 over x ln 3, and the derivative at k is going to be specifically 1 over k ln 3. See? So which is it? Is my slope log base 3 of k over k, see the top of the board, or is it 1 over k ln 3? It's both, right? I got this by doing rise over run for these two mystery points. I got this by doing the derivative at k. These should be equal to the same exact line. So now let's set them equal and see if we can solve for k. All right, so we have log base 3 of k over k equals 1 over k ln 3. If you cross multiply this, you get k ln 3 log base 3 of k equals k. You'll notice that the k actually cancels out, leaving you with ln 3 times ln base, log base 3 of k equals 1. In other words, log base 3 of k equals 1 over ln 3. But remember, this left side just means ln k over ln 3 is all it means. Change the base rule. Now these cancel out, and we're left with ln k equals 1. What is k? Nope. E. K is E. Ah, Okay, so we do know where that point is. What we were struggling with was we did not know the coordinates of that second point. So we were calling it k comma log base 3 of k. But now we know exactly what this point is right here. Although the one on the left was simple enough, that was 0, 0. We now know the one on the right is at e comma log base 3 of e. Now we can do the slope. So m is rise, log base 3 of e minus 0 all over, run, e minus 0. So the answer is log base 3 of e all over e. Or you can write it other ways. You can write the top as ln e over ln 3. And since ln e is 1, you just get 1 over e ln 3. This is a tough problem for many reasons. One of the reasons it's tough is because the way it was written was very generic. Like you just had to start drawing, and then you realize you don't even know this one point. It's like a missing point, so you have to make sense of it. So my general strategy on that was, let me just review it. I believed that this was the point k log base 3 of k. I knew that. I knew the slope then would be rise over run. But at the same time, it has to also be the derivative at k. So I found the derivative at k, and I said equal to rise over run. And it was kind of an arduous road from there. But the ones in your homework are easier than this. Although similar. One of them was like that. Okay, let's move on. What happens if you're trying to find the derivative if, let's say, y is log base 5 of rad x? So let's just go back to finding some basic derivatives. What's the derivative of that? Well, first and foremost, this is a log base 5. So it's going to have a derivative structured something like this. There should be 1 over the inside, and there's an ln 5 there. Okay? In this case, the inside is a rad x, so we'll just put rad x there. And now we need the derivative of the inside. So remember, this just means x to the half. So y prime, or the derivative of that, I mean, would just be 1/2 x to the minus half. Okay, so the answer is y prime equals 1 over rad x ln 5 times 1 over 2 rad x. You'll notice that rad x is actually combined, and you get 1 over 2x ln 5. Uh-huh.
Couldn't you just simplify that out? Just do x to the 1/2 and then bring that in front of log 5?
Yes, 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 yes. Yes, he's very clever. The boy's clever. He says we could have just written it like this and brought the half out front. And then we could have done 1/2 times, and then this is just going to be 1 over x ln 5. Yes, very clever. Thank you. Don't forget your pre-calc, right? Some things can move around with logs. It's true. It's true. Good eye. Good job. Sometimes I see that stuff and sometimes I don't, you know? Let's try another one, a little harder one. So here's an alternate solution. Good job. Okay, let's try another one, a little bit harder. This one is find y prime if y is log base 3 of 1 plus x ln 5. Okay, so first and foremost, we're dealing with a log base 3. So you're going to have 1 over the inside, and there's going to be an ln 3 here. There's nothing you can do about it. It's part of the derivative of the outside. Now we're going to get in there and look at that inside. Don't be scared by this. ln 5 is just a number. So 1 plus x ln 5 is kind of like saying, 1 plus 1.5x. The derivative of the 1 is 0. The x has a coefficient, it's like 1.5x is what it means. So this is just ln 5 is all it is. The derivative of this whole thing is just ln 5. So here's your answer. Okay, and then tomorrow I will show you how to find the derivative of something like x to the tan x. Bear with me for 1 second. I'm going to do the solution for this as soon as you leave the room and post it on YouTube. And so you can just watch it tonight if you want. Or you can follow the book and they do this example. Either way, this will be what our warm-up looks like tomorrow. All right, have a nice day. Okay, if you're asked to find a derivative of something like this, x to the tan x, you can write it like this if you want, because we're going to plan on using implicit differentiation for this. I would put an ln on both sides, like this. And the convenient thing about using the ln here is you can bring this tan x to the front. So it would look like this. So no longer does it look exponential at all, and now we can just use implicit differentiation. So let's take the derivative of the left side. Derivative of the left side is 1 over y prime. The right side is a product rule. We have a u and a v. So let's set up 4 parentheses for that. We need u prime v and v prime u. So I meant to write u prime there. There we go. U prime v plus v prime u. Okay, so u prime is going to be secant squared x, and v is ln x, and v prime is 1 over x, just learned that today, and u is tan x. Okay, so here we have 1 over y prime equals, and then we have sec squared x ln x plus tan x over x. And now let's just multiply both sides by y. So we get y prime equals y times sec squared ln x plus tan x over x. And remember, y was given initially to be x to the tan x. Forgot my x on the secant there. Secant squared x ln x plus tan x over x. So my strategy on this problem was I didn't like the exponential nature of the problem, so by putting in the red ln's, I was able to get rid of the exponential look and turn it into a all non-exponential problem.